औज़ुबिल्लाहिमिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम। कैसे हैं क्लास? आप लोग खैरियत से हैं? अल्हम्दुलिल्लाह मैं ठीक ठाक हूँ। उम्मीद है आप लोग भी ठीक होंगे। अच्छा जी, इन टुडेज लेक्चर वी विल डिस्कस द प्रॉब्लम्स ऑफ द लास्ट लेक्चर or the last chapter that we have been finished in the last video lecture, and I hope that you all will be understanding the lectures as well. We have inshallah arranged the Zoom session in a day or two. I will inshallah inform you all. Okay, going to the lecture right now. First problem is we have to find the null to null beam width of the broadside array. I've told you that null to null beam width is the distance between the maximum radiation pattern or the center one radiation pattern which has the maximum value. The difference or the strength of this maximum radiation pattern in the graph is called the null to null beam width, and it has been described before that broadside array is an array in which the uh, maximum radiation is perpendicular to the axis of the array. So we have to find the null to null beam width of that broadside array. Here we have given the length of the antenna is 10 lambda and the number of radiators or the number of arrays are 20. First we will find the d, which is L by n, that is length over number of radiators, which is equals to 10 pi by 20, sorry 10 lambda by 20. It will give us the value of lambda by 2, that is the half wavelength, and the formula for the bandwidth is, formula for the beam width is 2 lambda by nd. That 2 lambda we have n, that is 20, which is given in the question, and the d is the, we already been find out, lambda by 2. So 2 lambda by n, which is 20, and d is lambda by 2. Put on the values in the formula, we will got 1 by 5, which is equals to 0.2. That means the beam width of this particular antenna has the value of 0.2 radians. The next is the same antenna configuration, that is the broadside array antenna, and here also we have to find the null to null beam width with the length that is equals to 20 lambda and n is 50. So first we have to find the value of d, which is 20 lambda divided by n, which is which has the equation of L by n. We have L 20 lambda and n is 50 here, so it becomes 2 by 5 lambda. Then we have the beam width equation, which equals to 2 lambda by nd. We put on the values of n and d, which is given is 50 for n, and d is 2 by 5 lambda. The value after solving for the beam width will be 0.1 radians, which considered to be a very less value. Now moving on to the next question, that is we have to find the null to null beam width of end-fire array. As it has been told before that beam width is the maximum radiation pattern occur at any angle, and end-fire array is defined as the array antenna whose radiation pattern is maximum at the side parallel to the array of the parallel to the axis of the array. Here, in the last and broadside is the perpendicular to the axis of array, and fire is the parallel to the axis of array. Here we have given the length 10 lambda and n is equal to 20. Beam width for the end fire is the formula of 2 under root 2 lambda by nd. First we have to find the value of d, definitely, which has the formula which is L by n, 10 lambda by 20. 10 lambda by 20, we put it directly into the beam width formula. We have n is 20. Then after solving the equation, it has the value of 0.89 radians, which is a very reasonable and a good value. So the beam width for this particular specification array antenna is 0.89 radians. Then the next question is, we have given an isotropic radiator with a frequency of 6 gigahertz whose beam is at broadside, and we have to find the null to null beam width where length is 10 meter, and we also have to find the directivity. So here we have isotropic radiator analysis that has generating broadside beam which has been defined earlier with a signal frequency of 6 gigahertz, and we have to find again the null to null beam width and directivity with the length of the array is 10 meters. First we have to find the wavelength, that is lambda, which is equal to c by f. That c by f is the wavelength which is calculated as 0.05 meters. Then the beam width formula, that is 2 by L by lambda, which is a general formula for isotropic radiator, which by putting the values give us the beam width of 0.01 radians. Then the directivity, which is equals to 2L by lambda for the isotropic radiator. It will give us the value of 2 into 10, that is L is 10, lambda is 0.05. After putting the values, D will be 400. That is the directivity gain, that's why it doesn't have any units. Moving further, so we have a uniform linear array antenna which has producing the end fire beam, and the working frequency of the antenna is 10 gigahertz. Number of radiators are 50. Distance between the radiators are 0.5 lambda. We have to find the excitation phase and the length of the array. First, for the excitation phase, we have formula that is minus beta d. Here beta is equals to 2 pi by lambda. We don't have lambda, so we have to calculate it from the frequency, that is 10 gigahertz. Lambda will be C by F. You directly put it the value as C by F. Then multiply by D, which is given that 0.5 lambda. We have put it all the values in the excitation phase formula, that is lambda and D. After calculating, we got the excitation phase as pi radians. That means the excitation phase required for the receive antenna is pi radians. That is, the angle should be received with this degree. For the excitation of the antenna, then we have to find the length, which is equals to nd. N is the number of radiators, which is 50, or number of arrays, which is 50. D is given as 0.5 lambda. We put in the values in the formula, that is L is equal to nd. The equations from far is 0.75 meters. So the length of the uniform linear array in order to work for this frequency with these parameters should be 0.75 meters, and the excitation phase at which the antenna will excite or receive the power is pi radians. Moving forward, in a question we have to find the actual loss, basic loss, where frequency, working frequency of an antenna is given as 10 megahertz, transmitter gain and receive gain given as 1.65 dB, and D is equals to 30 meters, and lambda we have to find LA/LB, that is actual and basic loss, where D is given as 30 meters, frequency, working frequency 10 megahertz, receive and transmit gain is 1.65 dB. From these parameters we can find lambda, which is C by F. C is the velocity of light, that is 3 into 8 divided by 10 megahertz. They give us the wavelength of 30 meters. Basic loss formula is 10 log 10 4 pi d over lambda whole square. Formula for the basic loss is 10 log 10 4 pi d over lambda whole square. We can write it in log, that is 20 log 10 of 4 plus log 10 of pi plus log 10 of d minus log 10 of lambda. In log, the things which are in over will be considered as minus. The things which are multiplying are considered as the plus. So by putting the values, we got the basic loss of the antenna is 21.98 dB. Okay, so the basic loss calculated in the dB is 21.98 dB. Now we have to find the actual loss, which is equals to basic loss minus gain of the transmitter and minus gain of the receiver. For this, we can also use 20 log 10. Sorry, no, we don't have to use this because it's it is already given in the dB. So we just have to put on the value, that is 21.98 minus 1.65 minus 1.65. It will give us the actual loss, that is 18.7 dB. So the actual loss is 18.7 dB. The basic loss is 21.98 dB. It's a very big loss, and that is the fundamental disadvantage of the wireless transmission, that the loss ratio is always very high in the wireless transmission. So moving forward to the next question, that is, we are given the transmitter and receive gain of the antenna equals to 1.64 dB. We have an antenna that is two dipole antenna. The gain is given, that is 1.64 for both transmission and reception. D, the distance between the array is 10 meters. Transmitted power is 15 watts. Frequency at which this two dipole antenna working is 60 megahertz. We have to find the receive power for this two dipole antenna. The receive power formula is equals to transmit power multiplied by transmit gain multiplied by receive gain multiplied by wavelength square divided by 4 pi d whole square. We have to put on the values, that is Wt which is given 15, Gt is 1.64, Gr is 1.64, lambda square is C5, that is C into 10 to the power 8 divided by 60 megahertz whole square divided by 4 multiplied by pi multiplied by d, that is 10 meters whole square. If we solve all of this, it will give us receive power that is very less, which is 63.87 milliwatts. These are very less power. So I think that is the lecture for today. Inshallah, we'll update or upload more lectures, and inshallah, we'll do our best in order to make you understand this subject. Thank you very much for watching the video. Take care. Inshallah, meet at the Zoom session. Allah Hafiz.